Let's look at this problem. A car and driver have a combined mass of 1000 kilograms. The car passes over the top of a hill that has a radius of curvature equal to 10 meters. The speed of the car at the instant is 5 meters per second. What is the force of the hill on the car as it passes over the top? So this problem is basically applying Newton's second law of motion to a vehicle that is moving in a circular track. So we are going to use something called the centripetal acceleration in order to solve this problem. So for example, uh, what is centripetal acceleration? So if an object is moving in a circle or a circular track, it could be just part of a circle. Then let's say that this is the circular track, this is the particle or the object, it moves like that. Then there's a force acting towards the center of this circular track. So for example, in this case there's a force acting towards the center of the circular track. As a result, there's an acceleration in that same direction. That's Newton's second law. If there's a net force acting in a certain direction, then there's an acceleration in that direction. So this force we call the centripetal force, and the corresponding acceleration is called the centripetal acceleration. Now, if the speed of the object is v, if the speed of the object is v, and the radius of curvature, that is this, like the distance to the center, if that is r, then I can write this centripetal acceleration, the magnitude of the centripetal acceleration, as v squared over r. That is speed squared over the radius of curvature, or simply the radius. So this gives the magnitude. Since acceleration is a vector quantity, it's always directed towards the center of the circle. So this is the technique, this is the equation that we are going to use along with applying Newton's second law of motion to this problem. So when you read the question carefully, you should understand, okay, this is an application of Newton's second law of motion, and specifically I have to use this idea called centripetal acceleration because the object is moving along a circular track. The hill can be assumed as a circular track. So let me first draw a simplified figure just to make this more clear to you guys, and from there let's proceed by applying the equations as well as drawing something called the free body diagram. So the first thing what I'm going to do is that I'm going to draw a sketch of this situation. So this is like the hill, an approximation of the hill, and when the car plus the driver is at the top of the hill, it has a speed of 5 meters per second, and the combined mass of the car and the driver is 1000 kilograms. Okay, the radius of curvature of this hill, that is given as 10 meters. Okay, now what we need to do is that this is the object, this is the hill, so they are in contact, so there are definitely forces acting between these two systems. So we need to figure out the free body diagram for this driver plus the car system. So here I'm going to draw the free body diagram. So this is a very important thing that when you try to solve physics problems, especially problems related to mechanics, drawing a free body diagram is extremely important. So let me represent the driver and the car by this dot. The weight of the combined system is always acting downward towards the center of the earth. Let me represent that by mg. And since the car and the driver is in touch with the ground or the hill, there's a reaction force exerted by the hill on the car, what we call the normal force, and that is in the upward direction. So if you look at the car plus the driver, this is the free body diagram for the car plus the driver. The weight of the car plus the driver is acting vertically down, and the hill is exerting a force upward on the car and the driver, and that's called the normal force or the reaction force. So this is the free body diagram. Now the next step is to use a convenient coordinate system. That is, we are dealing with accelerations and forces, so we need to think about what direction is the positive direction, what direction is the negative direction. So since this is vertical, what I'm going to do is that I'm going to specify the positive side of the vertical direction. I'm going to define upward direction as plus y. So then definitely you know that the downward direction is minus y. Okay, so I have used my coordinate system, a convenient coordinate system where upward direction is the positive y direction. Now, since, as I told you before, since this is moving in a circular track, circular path, there's an acceleration acting on the object, and that acceleration is towards the center of the circular track, and that is what we call the centripetal acceleration. So the acceleration in this case is towards the center, so that means in the downward direction. Okay, so now these are all the information that I need to apply Newton's second law of motion. So I have all the forces upward and downward. I have defined my coordinate system conveniently, and I also have the acceleration acting on the object which is pointing downward, the centripetal acceleration. Now I'm ready to apply Newton's second law for this system. That means the car and the driver. So Newton's second law, F net, that is a vector quantity, equals mass times acceleration. Now since I'm only looking at the y direction, I can simplify this as all the forces acting along the y direction equals mass of the object times the acceleration along the y direction. Now all the forces acting along the y direction, I just have only two forces. One, the normal force upward, and the weight which is downward. So up is positive, down is negative. So I can expand this as f of n. That is my positive force in the upward direction, and since weight is downward, I'm going to put a minus sign representing the downward direction. Equals mass times acceleration. That means centripetal acceleration, as I told you before, is a of c equals v squared over r. But now the important thing is that this acceleration is downward, so downward direction is considered negative. So remember, this is very crucial. I need to put a negative sign because of the way I have selected my coordinate system. Okay, v squared over r, but it's a negative value. Now symbolically I can simplify this expression, this equation. I can take minus mg to the other side. I have mg minus m v squared over r, and then this is the simplified version. So now I can basically substitute the numerical values. So I'm going to write it over here. The reaction force exerted on the car by the ground, the normal force, is equal to f of n equals 1000 times 9.8. That is the gravitational acceleration close to the surface of the earth. We consider that as 9.8 meters per second squared, minus 1000 times v squared, that is 5 squared over 10 meters. Okay, so when you simplify this, you will get, you can use a calculator. This is 1000 over here. Remember that, there's a 1000 here. So you are going to get 7300 newtons. 7300 newtons would be your answer. But remember, this is just the magnitude of the force exerted by the hill on the car. However, if we consider the direction, it's upward, in an upward direction. Okay, so that's how you solve this problem. You figure out the force using Newton's second law and the fact that when an object moves in a circular track, uh, that object is experiencing an acceleration towards the center, which is given by v squared over r, what we call centripetal acceleration. So this is your final answer for this problem. The force of the hill on the car is 7300 newtons magnitude wise, and its direction is upward. So that's how you do it. And if you have questions, please comment them below. If you like this my presentation, hit the like button and subscribe to my channel. I'll be posting more similar example problems in physics as well as in mathematics in the near future. So I'll catch you later. Bye bye and have a nice day.